Thank you. Hopefully everyone can hear me. Good afternoon. My name is Blake Kendrick. I'm from Renishaw, and today I'll be giving you a short presentation on the work that we're doing with automating industrial automation. I apologise to those who may be online. I'm not connected to the internet, so I'm not actually currently sharing slides, but if you can hear me, hopefully my words will paint 1,000 pictures. Anyway, a little bit about Renishaw. I think most people here will have heard of Renishaw. It's been alluded to and mentioned a few times so far in the presentations this morning. We're a FTSE 250 company based in the UK, and our main focus really is on transforming manufacturing efficiencies, raising product quality, and optimising production outputs. We've got over 5,000 employees, and we're based in many countries, many locations within these countries, as you can see on the slide here. Now, a little bit about industrial automation. So this is very much a growth market. It has been growing at a steady rate over the past 20 years, and in the past 10 years there's been an even greater acceleration. You can consider industrial automation and industrial robotics really in three main sectors. The primary market consists of 5 countries: Japan, China, USA, Korea and Germany, and they make up about 70% of the market back in 2012. Then the secondary market, which is the next run of 10 countries, and then everybody else. So around about 160,000 robots in 2012. You skip forward 10 years, there was an increase of 350%, and well, the growth of the red segment there tells a story in itself. Due to policy changes in China, there has been mass adoption of industrial automation, and now China itself accounts for over half of all industrial automation installations in the world. And that has bumped the primary market up to just shy of 80% and squeezed the secondary and the rest of the world sector as well. I should say that's not to say each of the other individual countries haven't grown. They all have grown as well, but maybe not to the same extent that China has. Renishaw have been involved with automation for many years, both with our own internal manufacturing processes, but also with our customers that we've worked alongside. And in doing so, we've noticed several major challenges, and using our techniques and using our practices, we're able to address many of these. So these can be split into 5 different segments. The first is that of setup. So I'm a factory owner, and I want to set up automation within my facilities. I've given it the green light, but the actual act of setting up robots, and setting up automation lines, is nothing but manual. It really is not automatic at the moment. It involves skilled and unskilled human effort to put it in place and have manual checks. Once you have your system set up, you then need to make sure that when something goes wrong, and it will go wrong at some point, that you can recover quickly and efficiently, get that cell up and running with hopefully as minimal skilled human intervention as you can get away with. Next, drift. You need to be able to understand the performance of that cell over time. Now, that could be over the course of a day. If you have variable payloads and things are changing over the course of a shift, you need to make sure that when you are pointing the point of interest, the TCP, at the start of that shift, it will still be going to where you want it to at the end of the shift. And equally, over a longer time period, you want to make sure that as these electromechanical systems wear, that they are wearing in a predictable way, and you can repair and recover them before they have a fatal occurrence and are completely out of action. Then inaccuracy. Robots are very repeatable. They've been designed well since their conception 30, 40 years ago. You can get repeatability unidirectionally in less than 10 microns. However, they are very inaccurate. You want it to go to one position, and it's unlikely to do that. So often within more than a millimetre, which is a country mile in Renishaw tolerance standards. And finally, service. There is no automatic way of keeping these lines up and running. It really is archaic, and as actually a feast for all the senses. You want to check your robot's working correctly, you go and shake it, you go and listen to if it's rattling, you smell if it's burning in the motors, and then there's no traceability as to when it was repaired and to what level it was recovered to. So being able to provide a professional and consistent approach to that is really essential to take this part of the growing market to the 21st century. This is where we bring in our new RCS product range. These are a range of ball bars and probing sensors in order to either be used as tools in toolkits, so taken to a line, used to fix a problem and then take to the next job, or for permanent installation in order to get more out of a automation cell. The L90 is a ball bar, and those who may be familiar with Renishaw ball bars, similar concept. It is a linear measurement device. It's a very accurate ruler. It measures distance between two balls, one of which will be mounted in front of a robot, the other mounted onto the robot itself, and the various movements that you are telling the robot to do, you can then infer information and an understanding, both in terms of setting up the robot, but then in terms of range of diagnostic tests to see how it is performing over time. As an example of what I was saying before, the current method to set up a robot is once you've bolted your robot onto the floor, to manually drive a pointy pin on the end of the robot and a pointy pin in front of the robot together by eye, come at it from different directions, and then hopefully it's roughly within where you need it to be, probably to within a few millimeters. This, in contrast, is our approach, where you put in the ball bar, you're able to quickly jog the robot through a few different movements, and if this has already been set up and you know there's no collisions, this can be completely automated and rerun at a future date. And then once that is achieved, your TCP, your tool center position of the robot, is found and can be run from again in the future. The natural extension to a single ball bar is to have 3 ball bars. This gives you 3D information and can be used to, within its smaller working volume, understand the path performance of the robot or whatever is connected to the tripod system itself. This is good because if you're telling a robot to maybe draw a path and it's not quite achieving that because of the loading on the robot, you can hook this up with the actual loading that is used for the application and see exactly what its performance would be given those conditions, and then use that to calculate a more efficient path to achieve what you're hoping to get out of it. The second aspect of having a tripod system is we're also able to update the joint offsets. So that's the 0 positions each of the joint axes within the industrial robot. By moving it through a series of different locations and positions, we're able to output the true 0 position mathematically of the robot, and in doing so, the vast majority of the error which the robot sees can be updated and removed. This also allows a smaller form of calibration to be achieved within a factory environment, which is quite hard at the moment with the necessity of laser trackers to achieve similar things, and availability, cost and skills associated with using them means it's often prohibitive in order to do so. The other advantage of this as well is if your robot has been set up and the joint offsets aren't where they should be, you can use this kit to understand its current status before then returning it to that previous status once a repair work has been achieved. If you didn't take that approach and you basically went to a factory default, you'd have to end up reprogramming the robot in its entirety, which is very costly in terms of time. A typical process flow to take you through would be when you first receive the robot to run a volumetric test, so understand how well the robot is performing, do a joint offset update, and then check how that's improved it. Then, in terms of actually setting up, doing the TCP setup, which I showed before, and then using the ball bar over different locations within the working volume to do a part frame setup as well. Then, in terms of continuous maintenance, you can understand the global and individual joint repeatability and hysteresis, and at the point of a repair, do a baseline recovery and then a verification test to check if it's working as intended. Here's a real-world example of some of the data which we ran for a customer a few months ago. As you can see beforehand, the circular performance was more kidney bean shaped. You can see how this is plotted against each of the individual axes moves, and that helps identify reversal spikes and backlash. And then by understanding that and by running a joint offset test, which you see at the top, circularity and performance of the robot was very much improved. You can see the form error change is about factor of 8, I think. That's it. But it was a gross improvement from where it was previously. This brings us on to our permanent installed approach. So using our range of probes and sensors, which Renishaw obviously have a lot of, we're able to get the most out of robotic systems by increasing their accuracy by locally dataming what's going on. Another important aspect of this is the recovery. So if a robot crashes and something goes wrong, you want to make sure that it can be recovered to its previous state. We can do this by putting in location mounts, which spheres can be added to. Then at any point, a probe can be added to the robot itself, and that cell or several robots within a cell can be recovered back to their previous understood state. If instead you want to have the probe permanently installed, that gives you more accuracy than you could achieve from other vision-based systems, and when in combination with the tool setter in front of the robot, you're able to not only update the robot itself, but also the part frames, so you're closing the metrology loop around the entirety of the cell. Another interesting application for this is the emergence of machining on robots, and there's a lot of interest in industry on how to achieve this, because you're, in an ideal world, getting the best benefit of a much larger working envelope, but also the reduced costs when you're comparing it to a traditional 5-axis CNC machine. One of the main issues is calibrating the spindle, because not only do you need to know its point in space, you also need to know the direction, the vector in which it is pointing in. We've got a tool setter with a piece of software which is a generic approach to this, and as you can see in the video which is playing, that spindle has been located, then the probe on the robot is working out exactly where the part, which to be deburred, machined, or whatever subtractive activity needs to be achieved. And then as you understand where the part is in 6 degrees of freedom, as you understand where the spindle is in 5 degrees of freedom, you're able to then accurately do what you're achieving. This also, both in terms of the ball bar approach and the probing approach, makes digital twins actually practical. Whereas theoretically, digital twins are great, the main stumbling block is tying the digital world to the physical world and having the reliance of dedicated sensors in order to tie the two together. And in doing this, you're able to actually program offline and be confident that when you transfer your programs to the real world, they will run as intended. I mentioned some applications. There are plenty of other applications which are currently not really considered with industrial automation, but the starting point is there. And as you're able to move the accuracy further and further down, you're able to unlock several more of these applications. So laser welding, milling, deburring, 3D printing, composites, and precision assembly are all areas which could really make use of this technology and make use of robots in the future. Interestingly, about the milling, which I mentioned before, one area which I think really isn't explored in academia or in industry are the cutting parameters and performance of spindles and milling on robots. We've got a century's worth of information on how to do it on nice, stiff, traditional Cartesian machines. We really don't understand how to effectively do that on a slightly more flexible robot. So I think, yeah, that's going to reinvent how we take that approach. So we've had a successful product launch over the past year. These went out to the market last year, and we have had lots of positive feedback from integrators, making their lives easier, getting robots in place, but also end users and OEMs. So what I'd really like to do and end on, so we're running short and no time for questions. If anybody has any questions, please grab me during the next coffee break. Also very interested if there are any ongoing research opportunities within the sphere of industrial automation, and open to any potential collaborations in the future. So thank you all very much. It's been a pleasure presenting.
An overview of the activities in Renishaw. If you have got any questions today, I've got 1 minute for a question.
I'll ask one. Hi Blake.
Hi Steve.
Blake, are you updating information within the robot controllers based on the information from your work? And are you doing it in commercial controllers with their support, or are you doing it as a third party?
Yes, and we're doing it with their support.
So do you calibrate the geometrical model of the robot?
Yep, so there's different approaches of what we're taking, and depending on what needs to be achieved, there's different levels of calibration that we can do. We are further in communication with some robot OEMs than others, so we've got more access to some of the finer details. But most of it can be corrected through within the frames themselves, so either the tool frame or the part frame. But then we also then moving on to DHP updates and updating some of the proprietary models within the robot controllers themselves.
Just a quick question. Have you done this on an equator system at all?
Have I done this on an equator? Not on an equator, but we've used equators alongside it in order to help.
Equator's a parallel kinematic device.
Yes.
Which Renishaw. I'm just interested to see if you were trying to make equator more as a device that could be used.
Interestingly, so we currently support 6-axis industrial robots. We are soon to support cobots, which have a slightly different kinematic chain. Delta is up next on the list, and a lot of the differences in that kinematic model can be applied to a PKM-like equator.
Speak to Delcam, they used to say, but now I think it's Autodesk in Birmingham. Actually, they had a research project called COMET, C-O-M-E-T, that they were investigating the use of robots as milling machines. It was a European project 8 years ago. They have huge expertise. If you have any contacts, that would be great.
Interesting to follow on that.
Yep.
Thank you.
We do have a Renishaw lab here, a metrology lab, where we have the equator, and we don't have the robots though, but I think we have some Renishaw lab. We do have equators and CNF, so then we can come out with the lab.
Perfect.
Thank you very much.
Thank you.
Okay, so the next talk is from Renishaw 1 from the University of Manchester.
Renishaw used to own 25%.
Ah,
It made a lot of money.
okay. So they should know already.
It was my institution.
Okay. Yeah, there was a guy over there, Jan Willem Jr. Yeah, so he was doing a lot of robot machines. Lots of robot machines.
We're doing a lot with additive welding. That's when the project I finished 3 years ago.
Yeah.
They've been doing that there, and they've got the same model for welding and machining,
Okay.
which is good because it's the same data terminal additive as well as subtract.
Good afternoon, everyone. Nice to meet you all. My name is Wang Wang. I'm currently working as a lecturer in advanced manufacturing at the School of Engineering, the University of Manchester. So this is my first time to attend the CIRP UK General Assembly. I was really excited. I think at the beginning, I really need to say thank you to the organization community and all the colleagues from Cardiff that bring all of us together. About myself, so actually I was quite new to CIRP. I joined as research affiliate in August 2023. But actually I was somehow linked with CIRP, and I know CIRP for more than 10 years. So when I joined as a researcher, as an MSc and PhD in this manufacturing group in the year 2014, I was supervised, mentored by all of the CIRP fellows and associate members, and I also have some colleagues sitting at the corner over there.